in a combined, incoherent way, some chlorophylls are strongly coupled, and they form these excitonic domains, where we have split energy states, very fast, coherent relaxation, and then these domains will transfer from one domain to another domain, and at the end it will reach the reaction center, which is here called as a special pair. So these are evidently a very complicated system that needs well, complicated analysis. Now the two-dimensional spectroscopy was introduced in photosynthesis by Fleming's group on another complex, the so-called Fenner-Matthew-Olsen, which is a much simpler. It only has 7 or 8 bacterial chlorophylls. That's a bacterial antenna complex. So then it's also the first protein for synthetic protein to be crystallized, and many first things about it because it's quite simple. So this is the absorption spectrum, and it can be decomposed into 7 or 8 components, and then you can calculate the energy levels. So these energy levels, there are some. This is an exciton dimer. This is an exciton dimer, and then these two will transfer to another one. So you have kind of a connectivity like that. And when you measure the 2D spectrum of that complex, depending on the time, at early times what you observe is these diagonal peaks, you see, which correspond to the different excitonic energy levels in the system. But you also see some small cross peaks, even at 0 time, which tells you about which level is coupled to which level in an exciton dimer. And as I said, if you induce a waiting time, further and further, 200 femtoseconds or 1 picosecond, you start to see more cross peaks. Here, this is the excitation and this is the detection. So, if you excite, let's say in the high energy excitons, here, this is level 4, that's one. And after 1 picosecond, you can find population of level 1. So after 1 picosecond, the energy from here drops here. You get the idea. Now you can do that. This is a more recent experiment on the same system. You can see much clearly the excitonic bands and the cross peaks in the 2D spectrum. Now if we go back, let's do that, to the photosystem 2, and let's isolate the light harvesting complex. Only one subunit of the light harvesting antenna. It has chlorophyll B, it has chlorophyll A, 4 carotenoids, and you can sort of model the excited states. You have here these higher excited states from chlorophyll B, and then you have the lower excited states from chlorophyll A. And we did this kind of spectroscopy. Let's say we can tune the beam to overlap with those states, the excitation beam, and then the probe will detect all of them. So this is kind of a two-color to this experiment. Here is the chlorophyll B region, and this is the chlorophyll A region. At early times, we have chlorophyll Bs, and then at later times, they're no longer there because all the energy goes to chlorophyll A. Now, we don't have individual peaks because in the LHC2, in this complex, the energy differences are very small, so we cannot resolve different peaks. But we can still do model the dynamics. The first step is you can do a lifetime analysis of all the spectra, and you can get what is called the decay-associated spectra, which show you what is changing on certain lifetimes. So you have negative peaks, that means the population decays, and you have positive peaks, means here population rises. So what you see is energy transfer from chlorophyll B to chlorophyll A, let's say. And you can see here different states. If we excite at 650, or if we excite at 6 60 nanometer. These are different states. They have different dynamics, and they are coupled differently with the chlorophyll A's. So we can get some idea about the connectivity. Of course, the way to do is to excite the same and detect the same states. We can do that, obviously. And so this is the experiment in the chlorophyll A domain. That is at room temperature, but again, there is not much resolution. If you want better resolution, usually you lower the temperature. So, that's all I have as slides. Let's summarize what we can learn. The excitonic couplings in delocalized systems, we can see by off-diagonal elements in the 2D spectrum at early times. All energy transfer or population dynamics will appear as time-dependent changes in off-diagonal peaks in the 2D spectrum. If we can follow coherent dynamics, which will appear as oscillations in the off-diagonal peaks of the 2D spectrum. We can tell the homogeneous and inhomogeneous broadening from the diagonal and the anti-diagonal width of the 2D spectrum. We can follow the spectral diffusion by measuring the changes in the inhomogeneity over time. We can separate the bidirectional uphill and downhill energy transfer by comparing the symmetric cross peaks of the two sides of the diagonal. These are basic answers about our molecular system in a simplified way that we can get directly from the two-dimensional spectra. All right. Now, this whole talk is an advertisement. It's an advertisement to an instrument that does not exist yet, but is being built or planned at the ELI by a consortium of the BRC and the ELI mainly, and with the help from Page University. So in that we will use in the ELI we will use the advantage that they have is that they have very broad pulses that come at a very high repetition rate of 100 kilohertz with enough energy to drive any kind of nonlinear process. So that repetition rate and broadband is very helpful for two-dimensional spectroscopy because you have a lot of data points, a lot more than in transient absorption. So you need to either longer time or you increase the repetition rate. And that's it. More questions? Yes? Maybe after break, if you don't have now. Well, still waiting. Okay, thank you very much. All right then. So that's it for now. Happy lab tour visit in the afternoon. Yes.
Thank you very much for coming.
Thank you.
Great